Hello everyone. Today we discuss about the operational amplifier and its application. In this video we will only discuss about the application of operational amplifier, and different types of applications are elaborately discussed. Okay, so first of all, what is OpAmp? OpAmp is basically known as operational amplifier. Okay, so these electronics devices is basically, there are two types of applications. Number one, the operational amplifier used in a closed loop gain. When OpAmp used in a closed loop gain, the gain is finite and this value of gain is controlled by the circuit parameters. And number two is open loop gain. The operational amplifier, the open loop gain is basically infinity, and there are various circuit which is the application of this open loop gain, like a comparator, like a Smith trigger. These type of circuit are the basic applications of open loop gain. Students should be remembered that in an open loop gain the gain is infinity, and in a closed loop gain the gain is finite and determine the circuit parameters. The application of the operational amplifier in a closed loop gain, like a inverting, non-inverting, unity gain buffer, summing amplifier, differential amplifier, integrator, differentiator. So different types of circuits are the applications of in a closed loop gain. So first of all, what is the characteristics of an OpAmp? If we plot here input voltage positive, and this is a negative input voltage, and this is the positive output voltage, and this is the negative output voltage, so the characteristics look like that. These are transfer characteristics of the operational amplifier. Here we see that after some value of input voltage the output is saturated. So this region is known as the nonlinear region, and this region is known as the linear region. So this is the linear region, or the region where operational amplifier used as a closed loop gain, and this is the saturation region where operational amplifier used as an open loop gain. Okay, so this is the basic transfer characteristics. And one thing should be remembered, what are the ideal characteristics of an OpAmp? So this is only for the ideal characteristics. Okay, so this is the circuit symbol of the operational amplifier. This is inverting, this is non-inverting. Two inputs are applied and one output. Here two differential voltage are applied, V1 and V2, and these output are in a two mode. In the next video will be discussed elaborately. In the operational amplifier there are two voltage are present at the output. One is common mode voltage and another is differential mode voltage. Okay, so first of all, number one characteristics is for ideal OpAmp. So it is remembered that this is only for ideal OpAmp. That is, the input resistance R input should be infinity. Number two, output resistance R0 is finite or equal to 0. Number three is characteristics not drifting with temperature. Characteristics not drifting or not changing, not drifting with respect to temperature, capital T. Okay, so these are the basic characteristics of the operational amplifier. These are the transfer characteristics, this is the circuit symbol, this is the operation of the various circuit. So today we first discuss about the operational amplifier in a closed loop gain, and the first circuit is known as inverting amplifier. The first circuit is inverting amplifier. In inverting mode there one concept is known as virtual ground concept. So what is that? So first of all, this is the circuit diagram of inverting amplifier. This is output signal and this is input signal. Okay, so first of all, according to the KCL, here current is I1, here current is I2, and here current equal to 0. Why? Because the input resistance, here the resistance known as input resistance is infinity. That's why here is no current is flows. And due to the virtual ground concept, what is a virtual ground? Virtual ground means the ground where current equal to 0 and both voltage equal to 0. That is, both voltage and current equal to 0. But in a practical ground, the voltage equal to 0 but current equal to infinity. Okay, it should be remembered. It's very conceptual point in operation amplifier. So according to virtual ground, so there is a no current is flow. That means here voltage equal to 0. Okay, so now applying KCL, say this point equal to A. So at point A, if we apply KCL, then we get I1 equal to I2, because a simple equation, this I1 is entering this point and this I2 is outgoing from this point. So I1 equal to I2. So now what is the value of I1? V input minus 0, this potential at the point A equal to 0, divided by R1 is equals to 0 minus V0 by R2. So if we rearrange this equation, so V output by V input equal to minus R2 by R1. So this is the equation of this inverting amplifier, and this minus can indicate if we apply here one sinusoidal signal, then the output is 180 degree phase shift. Okay, the output is 180 degree phase shift. So this is the meaning of this inverted sign, and that's why it is known as inverting amplifier. Any signal applied in this input or gets amplified but 180 degree phase shift. And how much amplification factor is? The amplification factor is depend on this R2 and R1 value. R2 and R1 values. This ratio determine the gain of this circuit. Okay. Now next circuit is known as non-inverting amplifier. So what is it? In the non-inverting amplifier, there one concept is very important, which is known as virtual short. So what is that? So this is V0, this is R2. First of all, this is the circuit diagram of non-inverting amplifier, and here we apply our input voltage, and this is output. So now this input voltage, due to the short circuit of this terminal, here this V input also, the voltage drop across this point V input, because this terminal is basically short circuited according to virtual short. Okay, so now if we applying KCL, this I1 current and I2 current, the current direction depending on the KCL notation and also the circuit arrangement. So now at the point I1 equal to I2, again this is the point A. So at point A, I1 equals to I2. So what is the value of I1? 0 minus V input by R1, and this is V input minus V0 divided by R2. So if we rearrange this equation, so V output by V input equal to 1 plus R2 by R1. So look that here no negative sign is present, and that's why it is known as non-inverting amplifier. And the gain of this amplifier equal to 1 plus R2 by R1. Okay. So we see that in an inverting amplifier, the virtual ground concept is arise, and in the non-inverting amplifier, the virtual short concept is very important. Okay. Now, in the next, we discuss about adder, OpAmp adder. This is not a real adder. This is an application of analog adder circuit. Here we apply 3 resistance and 1 feedback resistance. This is known as RF feedback, and this is known as R1. This is grounded, and here 3 input voltage or n number of input voltage are applied. I consider here only 3 input voltage, but 4, 5 and 6 are also applied. This is an output. So according to KCL, there are 3 current I1, I2 and I3 which enter this point, and outgoing current is I5. So if we applying KCL at this point A, so we get I1 plus I2 plus I3 equal to IF. So what is the value of I1? I1 is V1 minus 0. Why this is 0.0? Because according to virtual ground, this point potential equal to 0. Okay, divided by R1 plus V2 minus 0 by R2 plus V3 minus 0 by R3 is equals to 0 minus Vf divided by Rf. So if we rearrange this equation, we get V0. So just consider sorry, so V0 equals to, so because both R1, R2 and R3 equal to equal resistance, so here we consider all resistance equal to R1, so that's why this is also R1, this is also R1. Okay, so that means the formula is Rf by R1 equals to V1 plus V2 plus V3. So here we get the addition of these three input voltage, but output is inverted. Okay, so this is the application of one error circuit, and if we consider Rf equal to R1, then this circuit is just addition of these three input voltages, but output is inverted. If we get the output is non-inverted, then here we are again connect one inverting amplifier with gain equal to 1. Okay, so that's why this negative equal to the positive sign applied across the output. Okay, so this is the adder and also known as Inverting amplifier. In the next circuit we known as differential amplifier. Differential amplifier is basically used for, is also known as substructor. What is it? The basic circuit diagram is here. We consider all resistance equal to the, here we apply two voltages V1 and V2, and this is the output V0. So what is the potential? The potential VA equals to V2 by 2, because here current equal to I and current equal to V2 by 2R, and the potential VA equals to I into R. So I means V2 by 2R into R. RR cancel out, so V2 by 2. Now according to KCL, in this point there are two one current I1 and one current I2. So I1 equal to I2. So what is value of I1? V1 minus VA. Why VA? Because according to virtual short, this potential is also getting here divided by R, VA minus V0 by R. So sorry, that means these RR cancel out. So for just simplicity we consider all resistance equal to R. Okay, so now V0 equals to 2 VA minus V1. So what is VA? V2 by 2. That means V2 minus V1. So output is, what is output? The output is basically the subtract of these two voltage V2 minus V1. So this circuit is known as the differential amplifier or the subtractor circuit. Okay, now in the next circuit is known as, it's a very important for different types of application, which is known as unity gain buffer. What is it? Unity gain buffer concept is coming from the non-inverting amplifier, because in the non-inverting amplifier we see that there one resistance is connected and another resistance is feedback. This is R2, this is R1, and here we apply V input, this is grounded, this is output. So what is the formula? 1 plus R2 by R1 into V input. So in this circuit, if we short circuit this, that means R2 equal to 0, and open circuit this, that means R1 equal to infinity. So that's why we just get output equal to input. So the equivalent circuit is, so this circuit also represented by this circuit. Okay, these are, we apply here V input and this is V output. Okay, so just V input we getting here, V input here. So this is a concept of unity gain buffer. Unity gain buffer circuit is application is the impedance for the impedance matching circuit, and different types of circuits are application in a instrumentation part. Okay, now in the next part we talk about the basic integrator circuit. Integrator. In the integrator circuit, in the inverting mode, we connect one resistance and capacitance here. This is capacitance and this is the resistance. Here we apply V input and this is grounded. So again, here current I1 and but here some problem, because in a capacitor there is no current is flowing, because capacitor only used for the storing the charges. So according to the capacitor theory, Q equal to CV, so current formula is equal to C into dV/dt. Okay, so that's why I1 equals to capacitor current. This is the capacitor current, just to consider. So I1 equals to V input minus 0 by R1, and this IC equals to, just putting this value, d into d by dt of sorry, d by dt of 0 minus V0. Okay, this is 0 minus V0. So here we V input by R minus C dV0 by dt. Okay, why 0 minus V0? Because here the potential equal to 0 and this is V0. So what is the V0? V0 is 1 by CR minus integration V input dt. V input. So the output voltage is the integration of input voltage. So that's why it is known as integrator circuit. Okay. Now in the next we talk about differentiator. Differentiator. What is differentiator? We just interchange the position of this capacitance and this resistance. So according to the theory, this is virtual ground. The potential at that point is 0. This is V input. So now in the input the current is C d V in minus 0. Why minus 0? This is virtual ground, is equal to 0 minus V0 by R. This resistance is equal to R. So now what is output voltage? The output voltage is CR minus sign CR dV by dt. So we see that the output voltage is a differential form of input voltage. So that's why this circuit is known as differentiator circuit. Okay. Now there are so many circuits which is known as log amplifier, which are applied in a closed loop gain, log amplifier, then anti-log amplifier, Logarithmic circuit are used for to convert high voltage to the low voltage, and anti-log circuit is used for in the reverse operation to convert low voltage into the high voltage. So basic logarithmic circuit is this. This is a logarithmic circuit. We connect one non-linear component which is also known as diode. Here we apply V input, here we apply V output, and for anti-log circuit this is minus, this is plus. Here we apply one diode, one resistance, this is V0, this is grounding, this is V input. So now what is the solution? The solution is that here in the virtual ground, here is the current known as I1, this is the diode current ID. So now I1 equals to ID. So what is I1? I1 is V input minus 0 by R. This is the value of resistance R. This is also R. And what is the diode current? The formula of diode current is e to the power QV by eta kt minus 1. This is a diode voltage which is known as VF. Okay. And this diode voltage is equivalent to the basically the output voltage. This is our formation of output voltage. Okay. So we neglect this one because this exponential term is very higher than this one value. So just these are and the output voltage is the reverse operation. These are negative because the diode N term is a P terminal and N terminal connected. So from this equation just solve the value of VF and then apply V0 equal to minus VF, and we get V0 from here. Okay, student, please solve it. And for anti-log amplifier we see that Is e to the power Q VF, this VF here equal to represent as a V input by eta kt minus 1 equal to 0 minus V0 by R. So from this equation, first of all we cancel this one because this terminal is very higher than 1, and then we calculate the output equation V0. Okay, so this is the concept of log and anti-log amplifier. This is very important. Okay, so this is the application of operation amplifier in a closed loop gain. Now we talk about the application of the operation amplifier in a open loop gain. So first of all, in open loop gain, there is a no feedback resistance are connected from inverting to output terminal, and here we connected one Zener diode for the reference voltage. This is a plus VCC, one resistance is connected, and here the Zener voltage are known as Vz, and here in this input we apply V input. So now what is output? And operation amplifier biasing voltage is plus Vc to minus Vc. So these are the saturation voltage. This voltage is also known as plus Vz, and this voltage is also known as minus Vz. Okay, so now this is our graph. Here input minus V input is output, this is minus V output. So at the certain point when V input is greater than Vz, then inverting terminal voltage is greater than non-inverting. So according to theory, the output is switches to minus Vz. Okay, and when V input is less than Vz, then Vz is greater than this, that means non-inverting is greater than inverting, then output is plus Vz. This is the general theory of comparator. So now the graph is look like that. Before Vz, the inverting voltage is lower than non-inverting, so output is plus Vz, and after crossing the Vz, the inverting is greater than, that means it is a plus Vz, this is minus Vz voltage. So these are the two saturation voltage. In this region V input is less than Vz, and in this region V input is greater than Vz, and this is just the transition region from transition to higher state, that means plus Vz to minus Vz range. Okay, so this is a basic application of comparator circuit. Now we talk about Smith trigger. So this is a Smith trigger circuit. In this video we just talk about the Smith trigger circuit. In the later video we'll discuss about the thoroughly calculations and procedure of Smith trigger circuit. This is V0. Here we connected one Zener diode, and here two feedback are present in the non-inverting terminal. One resistance is R2, another resistance is R1. This is R for Zener diode biasing, and here we apply one input V input. So this is the circuit diagram of Smith trigger circuit. In the Smith trigger circuit, basically there are two trigger voltages are applied. One is known as V1 and another is V2. Okay, so between these trigger voltage the output is switches from one state to another state. In the later video will be discussed thoroughly what are the mathematical calculation of this Smith trigger circuit. Okay, so this is the basic Smith trigger circuit. So in this video we'll just talk about the basic mathematical equations, not thoroughly about the internal structure of the operation amplifier. We just talk about the applications and the basic circuit applications of the operation amplifier.